So my name is Luca. I work at TrueLayer, as Wall, who spoke shortly before. My job is at the boundary between machine learning and software engineering, so I do a little bit of both depending on what is needed. TrueLayer, we build financial technology to access data securely, so mostly around banking data. And we also try to enrich those data to make them useful for the people who consume them downstream. We don't use a lot of Rust in production. We have some Rust for doing ETL pipelines, mostly log processing. Similar experience to what Federico was talking about before, 100x plus speed improvements. And we're looking into oxidizing a bunch of our web services. So if any of you is interested, that's a nice conversation to have. But I'm here to talk about something completely different today. So I'm here to talk to you about the intersection between Rust and machine learning. So in the Rust community, in the open source Rust community, what I mostly do is contributing and maintaining ND-array and ND-array stats. So some of the crates which are used to do linear algebra and matrix computations. And those are the building blocks of a bigger ecosystem that we hope is gonna flourish and thrive. And we're gonna see why we do see in this space an opportunity and when Rust fits in the bigger picture of the technology for doing ML. So just to get a little bit of a sense, also do a little bit of physical activity after lunch, who has done any machine learning, either for fun or at work? Raise a hand. Wow, that's a lot. Okay, so who has done it at work? Less hands. That's still interesting. Who has done it with Python? All. Perfect. That's the right audience. Okay, so for those of you who are not very familiar with ML, ML is a technology who has come, ML has an history which is extremely long, and depending on how you define the concept of being artificial intelligence and how many nested ifs you need to say that it's AI, we can go back 100 years or 200 years. But ML as a mainstream technology has probably reached the spotlight roughly 10 years ago, 15 years ago, especially in computer vision. And has passed from the pioneering phase, in which you had few organizations actually investing a lot of money and manpower in research teams who were validating the usability and the feasibility of this technology for commercial purposes, is now going mainstream. Like, there's so many tooling, the knowledge is so widespread, there's such a lot of interest, and there's so many products and services which you can build with ML features inside or ML at their core, which are useful, or sometimes are impossible to build without ML, that the business case for machine learning is basically solved. Like, we are convinced that machine learning as a technology has a use. So at this point in time, what we need to do is to mature as an industry. So to mature those set of tools, those set of practices, which actually allow us to do machine learning in production, machine learning for real, in a way which is repeatable, which is predictable, and which has some kind of engineering mindset. So we are, if you're familiar with the Gartner hype cycle, we are now in the slope of enlightenment. So we're slightly understanding how to best use and how to best manage this technology. So the question we need to ask ourselves when you have businesses of every size and kind using ML for their purposes is, are we set up, as it currently stands, to succeed? And what this elicits as a follow-up question is, what does it mean to succeed? So the ML community is a varied composition. So you might have people coming from software engineering, as well as people coming from more sciencey backgrounds. So you might have physics grads, maths, stats. And it might appear controversial, depending on who you talk to, but I strongly believe that what you are delivering when you're doing machine learning in the end is software. It's some piece of software, usually embedded in a larger piece of software, which is dedicated to doing something. So even though it has some peculiarities which are specific of ML and challenges which are specific of ML techniques, we should judge him at least as a basics with the same metrics we do use to establish what is excellence in software delivery. So I like these four, which come from Accelerate, Nicole Forsgren and others, which is lead time, so how long it takes from accepting that we're going to do something and having that something in production used by users. Deployment frequency, so how often we release code in production. Mean time to restore, how long does it take us on average to restore the production environment to a working state? And change fail percentage, so how often changing the production environment results in an unhealthy system or some kind of outage. Now, this talk is going to focus on two of these metrics, which are lead time and change fail percentage. And we're going to see why using Rust for ML has potentially big impact on both of those. So, if you're doing ML today, and the show of hands before confirms it, unless you're doing something very weird or something very peculiar, you should use Python. You should use Python because it just has a massive ML ecosystem. So whatever is the problem you're working on, as I said before, if it's not too esoteric, if it's not too cutting edge, there's a high likelihood that there's a package on PyPy somewhere, maybe with a weird name, it's an epsilon distance from what you need. And you can use that as a very good baseline to get started. And maybe validate whatever idea you're trying to validate, being that a product or an open source library. But Python by itself, in and itself, is not particularly suitable for doing scientific computing. Like there's nothing in Python as a language that makes it very good for doing heavy computations. What is nice about Python is that a nice general purpose high-level language is easy to learn, has a lot of penetration in the scientific community. There's a lot of people who can do Python. It's also general purpose, so you can kind of do at the same time the machine learning side, you can do the API, and everything can be in the full Python stack. This is nice. But what you usually want from a language that does scientific computing is being performant. So what happens is that you are not using Python. Like you try and you import this Python package, but what you're actually bringing in through the door is a bunch of C, Rust, C++ code, which are doing all the heavy lifting beneath the surface. You don't see them unless you need to see them, and they're doing all the work for you. And this is because Python is a good front end, so it's good to glue together and coordinate and orchestrate all these pieces of code, which require a lot of specialized knowledge to be written and be maintained. But Python itself has little control over resources, definitely difficult to control memory effectively. It's extremely difficult to do multiprocessing, correctly or incorrectly. Just doing multiprocessing is complicated, but it has a great FFI. So you can, speaking the C lingua franca, actually interface with other languages, which speak the C language, they can talk to each other. And this is a pretty standard practice. So all the big packages in the Python ecosystem, the NumPy, the SciPy, the Spacey, are actually just thin wrapper, thinner depending on the case, around some C core or C++ core. So the question is, what do we choose as the backend? So given that you might want to stay in Python land because you might want to use some packages which are available in Python, so there's a convenience, there's an ecosystem that you can leverage when you're doing Python. You want just to write the backend in something that is useful for what you're trying to do. Now, the requirements, of course, is that the backend needs to complement what Python is weak in. So Python is weak in performance. You want to do high performance type of workloads, so you need something that is fast and that is potentially you can control resources quite effectively. And the second one, which is not technical, but has the same big impact, is you want something that a reasonable, knowledgeable, competent person is able to use at the same time as you trust that person to do all the orchestration in the Python land. So you want something that a data scientist or a machine learning engineer, depending on how you want to call him, is able to use from the beginning to finish. In particular, the use case we have in mind is when what you're trying to do is not possible through the Python API. So what you often find, and that's been the case in some of my usage of Python, is that sometimes you take very convoluted and unnatural and unidiomatic patterns just because you're trying to call NumPy in a certain way because you want your code to stay in the C-wrapped backend. You wouldn't do that if actually Python was performant. You would do certain loops and certain things in Python. Or sometimes you have an algorithm, which is almost what you need. For example, using scikit-learn. You want to do, I don't know, the decision tree, but you want to change something. But when you try to look for the source code, that's actually in C, and then it becomes more difficult to actually go there and modify it. And what also is relevant is that a lot of the people who are doing data science and machine learning, especially the ones who do not come from a very strong CS background, do not feel confident enough to write C or C++ code, which is then aimed to go in production. So what you end up is people in a pipeline, each one doing one piece of the work, but this means that the lead time, as we were discussing before, so the amount of time it takes from the idea to the production release, is now compounded as multiple handover points, which means that usually it will take much longer. And if you need to iterate on whatever you're doing, it's going to take longer and longer. And this, as an industrial point of view, is not great. And here comes our Ferris Rust. So it gives us what we expect as the bare minimum, so good performance, great control over resources. But what is much more important? No, I don't have emojis. That's a big loss. So the compiler knows what I don't know. So if I give a task to a Pythonista, and bear in mind, I am a Pythonista, so this is my journey through Rust. Definitely not a person who came from a CS background. I can't code in C. If I gave to a Pythonista a task and saying, like, rewrite this hot path to this bottleneck in Rust. Now, it might take them some time, and the learning curve might be a little bit long, and what would take an experienced Rust programmer 10 minutes, maybe it takes them 2 weeks. But at no point in time, they're doing something that puts at risk their production environment or whatever they're working on, unless they're opting into using unsafe. The compiler is always there to watch that whatever you are trying to do is safe to do. Then you might go into logic errors, as Lorenzo was saying this morning, that is not going to be saved by the compiler. But then you can use all the other software engineering techniques. So you can use testing, you can use PR reviews, you can use pair programming, you can define by them. But at least I know that if it compiles, it's safe to run, which is a big thing if you come from a language where you don't have to manage memory and you're scared of pointers. So that's what I mean when I say that confident impacts the bottom line. Because if I can experiment in a safe sandbox, in an environment where I don't feel like I'm stepping on a foot gun if I free something or before or afterwards, then I can actually get more people involved because they're not scared. So there's a safe route from what the fuck is this? I've never done any system programming. I don't know how to do these things, to having done it once. So once you do it once, then you say, okay, so I thought this was impossible. It looked very weird, but I've done it once. It's running in production. No one has hacked us yet using a buffer overflow, so I can do it again. And again, and again, and again, which means that you might find that stuff you were not doing before was not before, it was not because it was not needed. So it was not because you did not need to modify that C piece of code. It was because you were afraid to do it. So there's much more that you can do and better patterns that you can enable once you actually can do the full stack. So you get more people in. You get lower barriers. You get more people in. These people form a larger community and solve one of the big problems in the Python community, that the people who are using the software, so the people who are using the NumPy, the SciPy, all these kind of libraries, are very different from the people who are maintaining the piece of software. And the intersection between those two, who can actually pass from being a user to a contributor, is not that big, which creates issues, because then those libraries, which are very complex, needs to be maintained. So if we can get more people getting involved into the community, then we can try different things. So the packages that we have are easy to maintain, and people can actually take bets and say, what if we do it the other way? What if we use this kind of pattern instead of this kind of design? And eventually, this will lead us to better abstractions, which will benefit anyone. So going back to the scheme I was talking about before, this is what I mean. It impacts lead time because you have fewer handover points, and you can get people doing the full stack of the work. And it impacts change for percentage because a lot of the things that usually would end up in production and causing issues are actually called the compile times. So you're left with the usual failures that you get in any type of software programming. So this is fantastic, and it's very inspirational, hopefully. But it doesn't tell you if you can do the stuff today, which is in the end what matters, especially when you go to talk to people who do ML. Say, yeah, that's fantastic. Like, can we actually do something? So yes, you can do ML today if you're willing a little bit to get your hands dirty. So you have what I call the building blocks. Building blocks as a set of crates which go and tackle the toughest places that when you need to start. Like when you want to do your decision tree, or more likely you want to do, I don't know, your nearest neighbors, you don't want to implement matrix multiplication. You want someone to have done that for you in a fast way that works and is easy to use. Now, the emojis have a meaning here, but I'm going to convey that with words. So what do you need for doing ML and data science? Those are the building blocks. So you need some data structures, you need n-dimensional arrays, and you need data frames. Data frames, for those who are not familiar, are a form of tabular data where you usually have columns of different types which represent dimensions. Very useful when you work with structured data, especially coming from SQL databases. So n-dimensional arrays, we have two pretty good implementation in Rust. There's nArray, which I contribute to, and there's nAlgebra. Both of them have been around for a while. Both of them are quite feature-rich. I would actually say feature-complete. So if you need to do something that requires an n-dimensional array, you most likely can do it with any of the two. The API might have some rough edges. Some of that is due to the fact that it's still probably not as wide used as an NumPy. So it requires a little bit of user feedback to make it smooth. And other stuff has to do with features which are not currently available in the language yet, which would greatly simplify certain things. Talking about constant generics, specialization, and so on and so forth, which hopefully should land by the end of the year. Then you have linear algebra, so the usual invert matrices, decompose, all these kind of things. Each of the two packages, so nArray and an algebra as a reference linear algebra crate that you can use. Even there, most of the common algorithms are there. Some of them bind to OpenBLAS. Others do stuff completely in Rust. So depending on what you need to use and how easy you want it to be portable, you can choose what you prefer. Statistical routines and the array stats, my little child, that allows you to do most of the most common routines that you use. So if you need to build something that is more complex, there you find most of the primitives that are sufficiently fast. The story is not so good when it comes to data frames and data formats. So data frames, there's been quite a lot of experimentation. I think at the moment, there's an ongoing discussion on GitHub, and we have, I think, 4 or 5 prototypes which are exploring different design choices. But there's no single implementation which is either feature complete, so it offers you everything you need, or is it the community choice? Like everyone believes that this is going to be the reference implementation. Because we're trying to sort out and decide what we want from the data frames, so what kind of features we believe are important, and where Rust can actually provide an API which is more meaningful and more usable than the Pandas API. Data formats in the sense of reading and writing data from different formats, especially with the purpose of talking to other ecosystems. So at this point in time, given the stuff that you have in Python, given the stuff that you have on the JVM, especially the big data stack, no ecosystem, no language ecosystem should and probably can be self-sufficient. Like you need to be able to talk with other ecosystems, and ideally you want that to do at zero cost as much as possible, so using the right formats to get interoperability. In Rust, we have Apache Arrow, which has been implemented, I think it's mostly feature complete, and we can use that, for example, as a base of our data frame implementation, so that when you want to switch to Pandas, it's actually just lightning fast, because you don't need to copy the data, you need to do any conversion, it's just there, you swap the memory. Now, the stuff gets even sadder when we get to the toolbox. Toolbox in the sense of the stuff you can go and plug and play. So import from scikit-learn fit predict. That is quite far away at the moment in Rust. All these steps, they're all areas of focus. There have been attempts in the past. So there are some crates, out of the top of my mind, I remember Rusty Machine, to say one, who tried to do especially classical machine learning algorithms in Rust, but they were probably too early in the game for doing that, because at that point in time, there were not a very strong ecosystem for doing n-dimensional arrays or for doing linear algebra. So they were trying at the same time to do the machine learning part, the n-dimensional arrays, the linear algebra, which of course was too much for a community that at that point in time was a little bit too small. So now that you have good building blocks, is the right time to try again. And these area of focus are not the products of my elucubration. So these are the themes which have been highlighted in this extremely interesting issue, which I invite you to check out, the one underneath, so Rust-ML discussion, when a bunch of people, and there are 90+ comments, about why people are coming to Rust, why are they interested in doing Rust for ML, what is the pain point they're feeling in the ecosystem they come from, and what areas do they believe that they can contribute, number one, and Rust can actually shine. So Rust can offer something which is not readily available in the other ecosystems. And those are the area of focus we have identified. And the thing that is extremely exciting if you're in this kind of space, is that there's a lot of people interested in contributing to this kind of effort. So while we were driving this discussion, which had a lot of people inside, in parallel, without us knowing, there was another proposal to open a working group. And when we found out, we were actually very happy. So it means that there's a need and there's a craving for actually getting this stuff started. And if we can get a working group, or if we can get something that is recognizable and people can reach to as the entry point to this kind of usage of Rust, that will speed up and provide a smooth path for people to actually get inside. So I'd like to close the talk with a little bit of a call to action. If you are a Rust programmer and you have never done ML, but you're curious and you want to learn, a good way to learn is to actually implement this stuff. And we might need some Rust expertise. Now, on the other side, if you're a Pythonista or a machine learning practitioner and you have never done Rust, but it looks really cool, and maybe you came to RustLab, we're also interested in talking to you. So we can mentor you and help you to get into the community. And that's exactly what happened to me when I started on NDRA. So probably all my PR reviews that I received from GTurner and BLAS were the best school for Rust for scientific computing. And that's the kind of vibe that we want to keep going, that we want people to feel when they come and try to contribute. And if you don't know either of them, neither Rust or ML, you're just very willing to learn, we can do that as well. So what we're looking for is interest, because we need time and a little bit of critical mass to actually get these experiments started. So I'm going to be here today, tomorrow. Just approach me. Questions?
Questions?
Find the path.
So when we do machine learning in production, we typically use, as you said, Python for the learning part or for the exploration and development part. But then once we actually deploy it, we use CUDA code or run the models on the graphics card. I think performance-wise, Rust would be somewhere in the middle if you run it on the CPU. So how do you see performance, purely performance-wise, really good argument for using machine learning in Rust?
Okay, so I think we're talking about deep learning kind of workloads, I do imagine, which is kind of a peculiar use case in the sense that you're running on a different type of hardware, and the Python libraries for doing deep learning, so the PyTorch or the TensorFlow, are of course running on engines which are heavily optimized for those kind of architectures. There's an interesting effort in the TVM engine, which is going to provide probably a way to run on different architecture with sufficient optimizations. And there's a group of people currently working on a front end in Rust and eventually also supporting it for training. So it's currently probably only supported for inference. It's not my greatest area of expertise, so I'm a little bit more focused on CPU-bound workloads, but there's definitely a use case there. They're probably the level and the quality of the libraries which are available in Python right now, and I would also add the amount of people and interest and corporate support of those libraries is different to actually match. So I wouldn't probably start a deep learning race with like a bunch of volunteers against TensorFlow. But eventually those architectures, especially as we develop more and more open formats like on NX, is going to be easier to get them on different kind of languages. So too early in the game, but not lost.
Any other?
Okay.
I think that's it. Okay. Thank you again.
Thank you.
Thank you.